Hi, ladies and gentlemen. We have finished up talking about oceans and really all the waters of the earth, and we're now moving on to talking about the actual earth itself, the ground, and what's under the ground. And so we're going to start that process by taking a look at the layers of the earth. So the earth is not one massive solid sphere. Instead, it is made up of many layers. And today we're going to start to take a look at that. And so by the end of our whole lesson, you should be able to describe what the main characteristics of each layer are, as well as being able to kind of draw a diagram or an illustration of Earth's layers. All right, we're going to start with the crust, which is the outermost layer. It's the layer we're probably most familiar with because it's the one that, when we walk outside, we stand on. It's the one our houses are built on. It's the one our buildings sit on, our cars drive on. So it is the outermost layer of the earth. It's kind of like if you had an apple, it would be the skin of the apple. It's the thinnest layer, kind of like the skin is the thinnest layer of the apple. You have the skin and then the flesh and then the core, kind of similar to the earth and its layers. But the crust is definitely the thinnest. Now, obviously, it's not as thin as the skin of an apple. But if you were to blow an apple up to the size of the earth, that skin wouldn't be quite as thin as it was when it was the size of a regular apple either. So it's still very much like that. It is actually made up of two different kinds of crust. We have what's called continental crust, which is the crust where the continents of the earth are. And then there's the oceanic crust, which is the crust of the earth that is underneath the oceans. It makes up the seafloor. All right. And the crust ranges in different thicknesses. It can range anywhere from 5 to 50 kilometers thick. If we think of it in terms of miles instead of kilometers, since many of us are not as familiar with being able to relate to kilometers, then we're talking about somewhere between about 3 miles thick and about 31 miles thick. All right, so at its thinner points, it's going to be closer to the 5 kilometers or the 3 miles, and at its thicker points where you have really tall mountains and things like that, it's going to be closer to the 50 kilometers or the 31 miles. So here we have a globe where we've removed the oceans, we've removed the water. So now we're just seeing the crust. We are just seeing the land itself, both the land that is the base of the oceans, the seafloor, and the land that makes up the continents. We've even taken away the vegetation, the grasses and the trees and things of that sort. And so the parts that kind of stick up there are either continents. For instance, here we have my brain just went blank. We have Australia right here, where you have these like pointy areas. Those are all mountains that are sticking up there. Okay. So we're going to focus in on oceanic crust to start with. And this isn't really in your notes, so you're just going to kind of sit back and take this in. But we're going to kind of talk about the difference between the oceanic crust and the continental crust here for just a moment. So the oceanic crust, it is thinner than the continental crust. You can kind of see that the continental crust sticks up more, so it is thicker. You can see that definitely down here with Antarctica. All right, and so that is the crust that is at the bottom of the ocean. It is more dense than continental crust. Why? Well, it's thinner and more dense because the ocean water is sitting on top of it. Water is really heavy. We talked about this back when talking about the oceans. We talked about the fact that when you go deeper and deeper into the oceans, the pressure builds because there is just so much water on top of you. Well, think of this crust. It has all this water on top, and that means that the crust is being compressed down. And so it is thinner because it's being mashed down, kind of like if you took a slice of bread and you put it between your hands and you just flattened it, okay? That would be kind of like what the ocean is doing to the continental crust. So it becomes much more dense because suddenly all that crust is in a smaller space because it's been compressed down. It is made up mostly of a rock called basalt. And it is, as I said, thinner than the continental crust. So it can range anywhere from 5 to 10 kilometers, whereas parts of the continental crust can get as high as 50 kilometers. Most of it's probably more in like the 20, anywhere from 10 to 30 or 40 kilometer range. 40 to 50, we're talking about really, really tall mountains there. And it's considered by many scientists to be younger than the continental crust. In other words, the crust is made up of plates. It's broken into gigantic pieces, and really, this unit that we're doing right now is called tectonic plates. But in order to understand these tectonic plates better, we kind of need to know about the layers of the Earth, and so these tectonic plates sometimes are crashing into each other, and sometimes they're moving away from each other. Under the ocean, they tend to move away from each other. So when they do, that causes a crack that magma comes up through. The magma, as soon as it hits the ocean water, cools off and hardens quite quickly, and that becomes a new piece of crust, new little bit of the crust. So as that continues to happen, you have more and more of this new crust happening. Keeping in mind, the magma still, was old. It just hasn't been hardened at the moment. All right, the continental crust, that is a layer of rock that makes the continents. For instance, the arrow here is pointing to the continent of Australia. We can see it sticks up above the oceanic crust. It is less dense because it is expanded more to make it thicker. It is mostly made up of the rock granite, although certainly lots of other rocks as well, but mostly granite. And it is thicker than the oceanic crust, as well as being older than the oceanic crust. Thicker because it's not being crushed by ocean water on top of it, right? So let's start to take a look at more of these layers. We've looked at the crust and what that is like. So now let's take a look at another layer, although it's actually kind of a couple layers combined. So the lithosphere. The lithosphere is the crust, and we include in the lithosphere the upper part of the mantle. So really, the Earth has 4 major layers to it. It has the crust, underneath that is the mantle, underneath that is the outer core, and underneath that is the inner core. The lithosphere is a special area that contains both the crust and the upper part of the mantle. All right, so it has the solid crust, which is rocky, and then it also includes the upper part of the mantle, which is not quite as solid, but it's still pretty rigid. It's fairly cool, all things considered, considering how hot other parts of the mantle can be. You can see here that the lithosphere would include this crust here, as well as this part here, which is the upper part of the mantle. The lithosphere can move around some. We'll talk about why in just a moment, but in this case, this piece of lithosphere, so crust and upper part of the mantle, are moving this direction. This part over here are moving this direction. They're crashing into each other. All right. And so when that happens, when they crash into each other like this, because the oceanic crust is more dense things we know sink. And so the oceanic crust actually sinks underneath the continental crust. We have the crust and the upper part of the mantle here, as they sink down into deeper parts of the mantle starts getting really hot, and so that crust starts to melt, becomes magma. Water kind of seeped into this crack as the lithosphere was pushing down underneath the oceanic crust was pushing underneath the continental crust. The water causes some superheating to happen in that magma, which causes pressure, which has to be released, and that goes up through a volcano. We end up with a whole bunch of mountains sometimes right along the edge of the ocean, and that is typically because 2 pieces of crust, oceanic and continental, are running into each other. The asthenosphere is right underneath the lithosphere. It again is fairly solid, but it's not like hard like a rock solid. It's weaker. It's not as rigid. In science, we say that it's a plastic-like material. We typically think of plastic as being kind of hard. You can typically take plastic and hit it and knock on it, and you can hear a sound. In science, when we say it's plastic-like, we mean that it's more like silly putty. It has some stretch to it. It has some movement to it. And so the crust, which is the lithosphere with the crust, which is sitting on top of the asthenosphere, is able to move because the asthenosphere is kind of movable. It shifts around. It's stretchy. And then the plates crash into each other. So at the bottom of your notes there, we're going to go back to your we're going to go back to your notes now, and we're going to take a look. There's a blank space down there where you can go ahead and kind of recreate this drawing or diagram of the crust, the lithosphere, and the asthenosphere. I'm going to ask you to pause the video and do your very best. I'm not expecting you to be a huge, wonderful, amazing artist, but do recreate this diagram to the best of your ability, making sure to label all of its parts. Okay, so hopefully you are now back and have finished your diagram. So we're going to take a look at the next layer, which is the mantle. All right, the mantle is the largest layer of the Earth. It is about 2,980 kilometers, extends down that far underneath the surface of the Earth. That is approximately 2,000 miles, a little less than that, 1,800 miles or so. It's made up mostly of silicate rocks, which have silicon in them, as well as having a lot of magnesium and iron. There's a lot of heat here, ladies and gentlemen, a lot of heat in this part of the Earth's layers, although not as much as we're going to get to in the next few layers, but certainly more than is in the crust. And so we know that heat causes things to rise. We kind of saw that in our lab that we did the other day. We saw that the hot water rose to the top or stayed at the top. So hot things, as it gets deeper into the mantle, the molten rock begins to rise. As it gets closer to the crust, it begins to cool down, and so then it starts to sink back down again. And so it causes these currents of rock. We've talked about currents in the ocean. It's not often we think about currents in rock, but this is liquid rock, remember? And so these currents, or this movement of the molten rock, is called convection or convection currents. And that's actually what causes the crust on top to move. As that mantle is kind of cycling up and down and around, it makes the crust move. So the crust is actually, in this case, when it's coming up this way, it's going to cause the crust to then move in this direction. All right. The average temperature of the crust of the mantle is like 3,000 degrees. All right, that is really, really hot. So again, it's cooler near the crust. It's hotter down near the outer core, but on average, it's around 3,000 degrees. All right, well, let's get our button to work here. Our next layer is the outer core. All right, it is the second largest layer. The mantle was the largest. The outer core is the next largest layer. And it is made up mostly of liquid iron and nickel. And it is in between the mantle and the inner core. And the Earth's magnetic field is actually created by this liquid metal moving around the inner core. As that liquid metal rotates around and around the inner core, it creates a magnetic field, and that's why our compasses point toward more magnetic north. All right. The average temperature in the outer core is about 4,000 to 5,000 degrees. It is really hot. All right, the final layer we're going to take a look at is the inner core. It is a solid ball of metal. Solid, no longer liquid, which seems a little crazy, considering how hot you're going to see it is in just a moment. But it's about 1,250 kilometers thick from one side of this metal ball to the other. Again, it is a solid ball of metal, and the metals are mostly nickel and iron. It is so hot in that inner core that it is what causes the outer core to melt. It's why the outer core is liquid. It actually spins faster than the Earth rotates. So we know that the Earth rotates on its axis once every 24 hours. That's what makes our day. The inside of the Earth is actually spinning faster than that. It's spinning inside of that liquid outer core. It is by far the densest layer of Earth. It is under a tremendous amount of pressure, which is why it can remain solid even though it is so incredibly hot. The average temperature is anywhere from 5,000 to 6,000 degrees. Because of its density, because it is so tightly packed together, it does stay solid despite those incredibly high temperatures. Typically, we would think the metal would melt and would become a liquid at those temperatures. But because the pressure is so intense, it stays as a solid.